Hello, in this video we're going to be looking at another example for tunneling, quantum tunneling, in this case using a different potential. This potential is of the type that we call Eckart potential. Now remember that this Eckart potential has this form for the potential barrier in terms of the equation for that potential barrier, and this is the profile that you will have, or that potential will have. So the problem is similar in nature to the problem that I posted before, but now we're considering that this potential has a height of about 2 electron volts, and this can be used, for example, to model a junction between two different materials, both of them being semiconductors, and the extent of that junction will extend over 100 picometers. So the main idea that we're trying to address here is that if I have an electron that is moving in one of the semiconductor materials, since we have this junction between those two, what is the probability that an electron that belongs in principle to the first material can tunnel through to now be on the second material? So that's kind of the question that we're trying to ask here. Now, the transmission probability in this case for the Eckart potential is going to be given in terms of hyperbolic trigonometric functions. There are two parameters I still have to define, x1 and x2, and those are given by this equation, where x1 related to the particle through the energy of the particle, x2 related to the height of your potential through this B0. Another thing that you have to note in this particular equation is that you're using the absolute value. This is what it means in the equation, the absolute value of this term whenever you find it. So let's do the proper substitutions once we know each one of those parameters. And at the end, we're going to be looking at first calculate, for example, x1. We know that we're referring now to an electron, so we can take the mass of that electron and multiply it by the energy of my electron. That it was given here in electron volts, but I converted into joules. And then I have the value of h bar. I have the value of the 100 picometers. That was the width of the potential, now converted into meters, and I find that x1 is equal to roughly 9. Now remember to do dimensional analysis, because in this case x1 and x2, according to the equations that I have, must be unitless. Now the second parameter that I can calculate is x2, and remember x2 includes this term inside of the square root that is a absolute value for whatever you are calculating here. Now, again, I have the mass of my particle. In this case, it's an electron. I have the energy of the barrier that was given here as 2 electron volts. I have h bar, and I have the width of my potential. And here I have h bar again and the width of that potential. So when I do all the proper substitutions and I do all the calculations, I end up with roughly 8.5 for x2. Now I take those two values and I substitute them in this particular equation, and with that I can calculate finally what the transmission probability is going to be. And what I find is that the transmission probability is 0.61, which is roughly 61%. I'm rounding up, but that's what it is. Now, one suggestion that I have for you in this particular case is compare to the value that you will get for that transmission probability if with the same parameters you use the formulation of the rectangular potential barrier. So do that as an exercise. Same parameters for the height of the barrier, the width of that barrier, and the energy of your particle, but now with the rectangular potential. And let's compare which of these two, the Eckart potential versus the rectangular potential, will predict a larger transmission probability. So something for you to have in mind. Let me know if you have any questions, and I'll talk to you later.